If you find the loopholes in the IoT system, then we can design any security. But my talk is not to the security today. What I am looking at the application of blockchain on the IoT. So IoT itself is a one domain. Blockchain itself is another domain. Now, how to synchronize these two domains? So that means how one domain can take a benefit of the another domain to solve some of the problems. So what I am trying to discuss the issues and challenges in the IoT infrastructure. One of the issues is that you come across with the security issue, but I will not be dealing with the security issues. Rather, I tell something on the security issue. But my more focus will be on how the blockchain is used to overcome some of the challenges of the IoT. So when we talk about the IoT and the blockchain, let's first discuss what are the challenges that the IoT is facing and how the blockchain is used to overcome these challenges. So let's look at the challenges. The challenges that the IoT infrastructure is facing can be broadly classified into 5 different domains. One is the system design, then management domain, whether it's a data management or it's a device management or it's a service management, and last one is the security. So I will talk on each of these. Now, if you look at the system design, the IoT infrastructure itself is a highly centralized infrastructure. Now, the moment you have a centralized infrastructure, any centralized infrastructure has its own demerits. So it's a centralized. All centralized infrastructure has some demerits. Then this comes with a performance bottleneck. We discuss all this. Then look at the problem with the data management. The IoT system is billions of devices, and a device generates huge volumes of data. And the data may not be exactly in the same format. So again, it challenges. So here also comes, you need to process the data. Once you process the data, you have to store the data. Then once the data is stored, then you have to mine the data to get some useful information. Now, if you look at the device management, you install billions of devices. Then how do you manage the device itself? So if you talk about the deployment, then this comes the maintenance of the device. Then the service management. Okay, the IoT network itself provides a service. So how to discover the service of your interest? How to discover the service? And once you have a service, then there must be a payment for every service. So how the payment can be made? So all these issues. Then the security itself is a very serious issue, specifically using the counterfeit hardware. So if you had install a counterfeit hardware, then through this counterfeit hardware you can launch an attack. But how to detect a hardware itself is a counterfeit hardware. It's a good challenge to detect a counterfeit hardware. Then how do you authenticate the devices? If prolong the communication among the devices, then if you have the data, there are another serious issues when you have a data with the privacy of the data. How do you maintain the privacy? So let's look at each of them. So when we talk about the system design, we can look at the IoT system itself or the device itself. Now let's look at from the device perspective. If from the device perspective, the underlying embedded system or any device that you have, you need to support an efficient, reliable, robust data collection and data transmission. That means any device, you collect the data. The data that you collect is must be a reliable one. And when you transmit it, during the transmission, there will be a data loss. There is a transmission, there is a possibility that somebody can tamper the data. So how do you protect this one? Tampering of the data loss. Now, if you look at from the system point of view, the entire IoT system point of view, then the device needs to satisfy the requirement of availability, scalability, flexibility, and the cost of efficiency. Now, by default, the IoT infrastructure is a centralized infrastructure. Now, when we have a centralized infrastructure, and any centralized infrastructure is a single point of view. So, if the centralized infrastructure fails, the moment the central infrastructure fails, the availability of everything fails. So, there is a serious issue. Now, moment it's a centralized infrastructure, then why do we have a centralized infrastructure? It simply says, why not to move towards a decentralized infrastructure? Now, moment we are moving for a decentralized infrastructure, then there must be a certain underlying technology that will support your decentralized infrastructure. And blockchain is one such technology. It's decentralized, distributed, and transparent technology. Decentralized, distributed, transparent technology that can support or overcome these limitations that the present IoT infrastructure is going to face or facing. Now, if you look at the from the data management point, you have the billions of devices connected, thousands and thousands of devices connected. All the device generates the data of the in a different format. Right? The formats are different. Now, when the formats are different, then how do you process the data? A automobile generates in a one format, a digital sensor generates in another format, any of the devices there in the system that also generates in different format. All formats are different. Volumes of data generates are different. Volumes of data are generated, and this data is generated not in a very specific format. When the formats are different, then how do you store it and how do you process it? That's another challenge. So data generated by a variety of devices are likely to have a inconsistent format and semantics. It can be a stream data, it can be a discrete data, it can be an image, it can be voice, it can be a video, anything. And the formats of all these data that are generated are also different. Now, in this different format, before you store it, there needs to be some pre-processing of the data. Data needs to be pre-processed. Either some compression to be done, some pruning can be done, or some leveling of the data can be done before it can be stored. It can be used and stored. Now, you do all this pre-processing. To do this pre-processing, you need a processing power. You need a processing power, but let's look at the underlying devices that we have. Does the underlying devices have that much of processing power to perform all these operations? These are all tiny devices. The underlying IoT devices are the tiny devices and they are resource constrained devices where you need to process. So pre-processing another challenges. How do you process it? So where do you process it? Why you do not have enough computation to perform? So where do you process it? So again, it's another issue. Now, it's not only the data that is collected. Data is processed. The another problem that comes, why do you store it? Storage is another major problem. Volumes of data, enormous amount of volume of data is created. And we send all process. Let's say processing capability is 3 lakh. Then why do you store it? Now, the IoT service provider, some of them may be able to store it, but not all of them can store it. So where to put it? Put it in a central server. Put it in a central server. The moment you centralize it, again, come back to the same problem. Availability is an issue. Single point of failure comes in the picture. Then comes the blockchain. Then you have the data now. Collected the data, processed the data, mechanism is there to store the data. Then what do you do with the data? The data needs to be retrieved. Now the moment you have to retrieve the data, so you need a data mining tool. So you need to have an efficient data mining tool to retrieve the data that you have stored. But the problem with the data mining tool is that with the if you had image data, right? It's a video data. So data mining tool may not be efficient to process the image and videos or another thing. Let's look at the device management. Thousands of devices are deployed. Now, moment you deploy the thousands of devices, how do you manage all these devices? Now, deployment, it can be a manual deployment. If it is a manual deployment, then you need a minimum resources to deploy it. If it is automatic, that's fine. You can use an automatic system to deploy it. So you can take the IoT device from sensor and throw it on a forest. Then you can use those devices to collect the information from the sensor. That's fine. The method of deployment. It's not the method of deployment that is done. After deployment, you have to maintain the data information in there. After the deployment, you deploy it. It's not enough. How to address it? How to name it? The naming scheme and addressing scheme has to be also taken into account. Now, you have the billions of devices. How do you protect the naming scheme? How to name and how to address it? Now, if you are changing the address, let's say you had a using IP person 4 for each of the device, and you need to migrate to the 2006. Then how do you migrate? So you need a tool. So must be automatic hardware and software must be available to move from one addressing or one naming scheme to another naming scheme. So again, there is another issue. Then deployment, naming, addressing. Then once you deploy, you had some credentials stored in it. Maybe the keys are stored for communication. Then how to protect the keys? The next question is deployment. Addressing scheme done. You need to update the software. You have to update the keys there. So how to keep the security credential, the firmware, the software of the device up to date. Now once you deploy, then updating this device is free. Or keeping the security credential is very difficult. Anyone can access into the device or access into the network, and he can tamper any of these security credentials. So if someone is able to enter into the network, IoT infrastructure, and he can tamper any of these devices, they can easily access the network and he can easily get confidential information from the network. So these are another issues. Now, if you have all the device, then there must be a control management of this device. There should be somewhere there should be control. Somebody has to control all this device. Now, if you look at from the traditional point of view, this is a centralized infrastructure. So there is a single entity who is controlling this. Now, from the centralized infrastructure, when you are moving to a distributed infrastructure, there should be some mechanism to control all these devices. So, and this device that you put or deployed in a IoT infrastructure, all these need to be traceable. That means you should be able to trace the location of the device. Or once you deploy it, it must be able to audit that whether the particular device is present or whether it is already tampered by someone. So it should be traceable, it can be auditable, it should be in a position to manage it, and all this maintenance mechanism should be available. Unless you realize you do everything, you are maintaining everything you are doing. I am looking at, I am able to trace it. So that is a traceable mechanism, which is an unreliable traceable mechanism. Or if you are managing the device, the entire management system is not reliable. You need to have a reliable mechanism for all this, and these are critical for any IoT infrastructure operation. Now you look at the service. So there is a service provider, and there is a user or the customer for the service. Who is the service provider? The one who is owning the IoT infrastructure is the service provider. He is providing the service. Now, when someone provides the service, and the service that is provided, you can allow to access any of the IoT devices. Assume you can access the IoT network. I am a customer. I can access the IoT network. There are two ways you can. Anyone can get into the IoT network, can access the service, or you need to control the access. Now, if you have to control the access, that means the customer or the IoT service provider is controlling the access to the IoT network. Now, when you are controlling the access to the IoT network, he is also providing a security to it. That is the infrastructure security. Anybody cannot access the IoT infrastructure any way he wants. So he puts a security to it. That means managing the infrastructure. So he is controlling or managing the entire access to the IoT infrastructure. So he is providing a security to it. The security is provided from the service provider. Now look at the extreme other end. You have the IoT service provider, and he says anyone can access. Anyone can access the IoT device. Anyone can access the data. Now, the moment anyone can access the device and anyone can access the data, then again comes. So, with security problem, then another issue is comes that every time if someone needs a service, because I need a service, so I need to make a request to the IoT service provider. So again, that's another problem. So the usage of services is to be based on the trust between the owner of the infrastructure and the customer. There is a trust relationship built between the customer and the service provider. Now, we look at one point how this trust can be built using blockchain. Therefore, to build this trust, a method to provide a transparent and reliable service discovery and usage is required. Now, to build up the trust and to query the network, you need to have a mechanism, a reliable service provider mechanism, which is transparent. The moment it is transparent, that means anyone can audit any transaction that is being. Then security. Security is a very serious challenge. It's a security challenge for all the networks, including the IoT network. Then the problem with this IoT is mostly they are tiny devices, resource constrained devices. So if you look at our traditional network, they provide a security mechanism where you do a lot of encryption. You use encryption technique, you look at digital signature, and look at all these protocols, the algorithms, underlying algorithms, they consume a lot of resources. They're computational resources. Now, I want to implement all these resource sensitive applications, which consume a lot of resources. Then, my resource constrained device, which does not have enough computational capability, cannot handle this, all this high-end mechanism. Right? So there is a problem. And if I will implement it, then I should download or degrade the encryption techniques. That means all functionality of the encryption may not be used during the communication with the IoT system. Now, while you are not using all the functionalities of the encryption techniques, that means your communication is not secure. You are not using all the functional encryption functional techniques, so the communication is not secure, or ATAL is not also encrypted. When the communication is not secure, so anybody can tamper with the communication. So there is an issue. So this low power, small memory, limited processing capabilities, and the low cost devices. This all puts implies a strong vulnerable potential. This low processing capability, low memory, and resource constrained device are more vulnerable to different types of attacks. For example, you had an IoT infrastructure, then you can deploy a counterfeit hardware. Look at the millions of devices are there. You have no way to authenticating all the devices. Anybody can put a counterfeit hardware. A counterfeit hardware is not authentic hardware. You purchase a device, then you can get a similar counterfeit device. So when you deploy a counterfeit hardware, that means you are opening up a backward door to launch an attack onto the system. So it is a problem with the counterfeit hardware. The most IoT devices are small, simple, and they are inexpensive to manufacture. Since they are inexpensive to manufacture, so it can be manufactured by many of the vendors. So the moment they manufacture the counterfeit hardware, they can deploy the counterfeit hardware. So once they deploy the counterfeit hardware, and through this counterfeit hardware, an intruder can launch an attack onto the system. Because these counterfeit hardwares are not well protected. They are not foolproof hardwares. The original hardwares are foolproof, but they are not foolproof. And this counterfeit hardware, they are sometimes manufactured from the electronic devices which are discarded electronic devices. In discarded electronic devices, there are some components still active or still in a usable condition. So they can use those components, reclaim components, and to build up this counterfeit device. So detecting the counterfeit hardware is another serious issue. You're talking of all the hardware issues. I'm trying to explain each of these hardware issues, so you have to find a solution. So I am not going to present any solution to that. I am looking at from the blockchain point of view. Look at how the blockchain can do it. You can have your the counterfeit hardware, and maybe someone will discuss in the talk basically on cloning functions, how these are being used for the hardware security. So they are simple to manufacture. And it can be easy for an adversary to counterfeit a popular piece of hardware and put a counterfeit hardware. It may happen that the adversary may itself put some botnet into the counterfeit hardware and use the counterfeit hardware as a botnet. And this is actually done in 2018. In 2018, some botnet or Mirari or something like that, I forgot. they launched an attack and it brought down most of the systems, including Netflix. Many systems are brought down for several hours. So it's possible. Then we had a device now. Now we had a counterfeit device. Then there is the mechanism to say that the device that is deployed are not a counterfeit device. Then once you device, then there must be an authentication for the device. How do you authenticate the device? So the now what is the different mechanism for authentications? Encryption is one, digital signature is another scheme. So now if you're using those schemes, these are resource intensive schemes. And when you have a low processing device, then you cannot use those schemes. So you have to find out a secure techniques which are low processing, require low processing capability. So the limited processing capability and the insufficient memory space also cause a problem. Device authentication. Device authentication using the traditional technique. So you need to find out some other mechanism. And the other mechanism without using the underlying architecture, the best will be the blockchain. I'm not changing anything. If you look at some of the almost all techniques we are not going to discuss, at least few techniques I'll tell you how the blockchain has been used for device authentication. Then if you look at the communication between the devices. So you need the communication protocols, and if you are using a TCP like of the secure communication protocol, again it requires enough resources. And we have a device which are basically resource constrained devices. Now, if there is a resource constrained device, so you cannot use a communication protocol which is going to consume a lot of resources. Basically, we are talking a computational resource in this resource constrained device. Then this handshaking and retransmission. Like if I'm using a secret communication, then basically what you do a handshake or you can do a retransmission. But these mechanisms cannot be used because these are low cost devices. And if I use this handshaking mechanism for communication, for secret communications, then most of my resources will be used to resolve the problem. So handshake and retransmissions impose a heavy load for device with limited processing resource and cause the wide congestion in the bandwidth. Now we talk about everything. There is another problem associated with generated data. We have created a data, processed the data, right? Traditional IoT infrastructure is a centralized base, the central authority. It's a single point of failure. Now it's not only that. Anybody launch to the central entity, then he can manipulate it. So there is a problem. So how to protect your data? So there comes a data privacy. Data privacy and user preference, like it's not only that data. User want to have his own device. Suppose I am a customer. I am a customer for IoT infrastructure. I can request the IoT service provider that I want to own a particular device, and I want to set my configuration to the device. How you do that? So this is again challenges. You are owning your own device or setting your own configuration. That's itself is a challenge. So privacy in user preference needs immediate attention as the personal and sensitive data creates. If you have the sensitive data and some personal information there, and if it leaks, somehow somebody gets into it and it leaks all the personal information, then everything is lost. So to do everything, the customer should be able to easily and smoothly obtain the data. You had the data, I should have a mechanism, I should obtain my data. All should be done smoothly. Change the preference. I have some preference on my data, I can change. I say I have some data, no one can access, and I want that my data is now useful, so I can want to share my data, so I will change my preference. So to be in a position to change those preferences. Or stop the service of each or argument. So I can stop some service. I had owned some resources, and the fine morning someone decided that he is not going to provide any services. So everything should be done by one. It's all should be done in a way so that no one could do eavesdropping or delay or interrupt the entire service. Now we talk about the challenges that requires building challenges in building a IoT infrastructure. Now let's look at whether the blockchain is anyway able to solve any of these challenges. Now, these challenges are being solved without changing your underlying infrastructure. I had my underlying infrastructure as it is. On the top of that, I am using some mechanism of the blockchain, how this blockchain can be built. Let's look at system design. So traditionally, a centralized architecture. Basically, traditional architecture is mostly a centralized architecture. So it's a highly centralized IoT architecture, and it has a problem. Any centralized mechanism has a sort of problem. Scalability is an issue. Then throughput is an issue. Security is itself an issue. Throughput is an issue. It's a central server. Then all the throughput depends upon how much bandwidth that we have. So it's an issue. Now, how it can be overcome? Now, we'll discuss about the blockchain. We'll discuss more on the blockchain and some of how the blockchains can overcome some of these issues. And blockchain is a distributed, decentralized, transparent system. So distributed, decentralized, and transparent system. So it's a distributed system. Blockchain can help to be a decentralized IoT system that can overcome some of the constraints that the present IoT infrastructure is facing. So it's a highly centralized one. Blockchain provides a distributed, a decentralized architecture. So from here, you can move towards the blockchain. Then you can get a decentralized architecture. Then blockchain basically is a peer-to-peer communication. So it's a peer-to-peer communication scheme in a blockchain, which is an ideal match for an IoT. And the blockchain solutions can provide an efficient, reliable, robust, scalable IoT system that can be operated over the blockchain. Now look at blockchain is a reliable one. It says it's provide more security. It's a distributed, decentralized, transparent. The moment you say there is a transparency, so there is a reliability. The moment you say it's a transparent, everybody knows it. When everybody knows it, there is a reliability in the system. So it's an efficient, reliable, it's a robust system. The robust system because you cannot tamper with the data of the system. It's not possible. It's called we talk about something called immutable ledger. We'll come back to that immutable ledger. So something once written, you cannot tamper without affecting the entire chain. So moment the chain is affected, then anyone in the chain can immediately detect there is somebody has tampered the data. But in a centralized system, you have the data. Intruder can get into the centralized system, manipulate the data. The user has no way of knowing whether the data actually is manipulated or not. So this doesn't happen in the blockchain. And it's a scalable. Blockchain basically is a scalable. Let's look at the data management. So we look at the system, we look at the data, and IoT needs a distributed and reliable. So look at what is the problem with the IoT. The problem with the data is stored, process, it collects the data, the volumes of data is more, process it stores it. When you store it, it's a centralized storage. Everything is to stored in a, since it's a centralized architecture, so everything is to stored in some central server. And the moment it's a centralized architecture, there is a single point of failure. So what we want, we need a distributed storage. And it's not only distributed storage. From the centralized storage, you move it to the distributed storage, absolutely fine. But what about the reliability of the data? Can you rely, because move from the central to a distributed system, you cannot claim my data is reliable. Instead of placing it 1 plus, you place it at 10, and next fine morning you cannot say, I placed it 10, so it's reliable. It's not possible. When it is distributed, you cannot say it's reliable, but blockchain just provides a reliability. The reliability comes from the blockchain because it's a transparent. So this is a distributed, a reliable data storage, and a blockchain can be used for it. A blockchain system can be used to provide auditable data storage for an IoT environment. Look at you had a data, you stored the data, and anyone should be in a position to audit the data, whether the data is valid or not. So this blockchain can provide. The blockchain can be used as an additional layer of cloud storage to provide data integrity guarantee. So integrity of the data. That means data during its residency, when it's stored, in the system, nothing has been changed in the data. That's from the data integrity. And blockchain can provide the integrity. So let's look at the device management. The problem with the deployment and the maintenance. We say it's a massive number of devices to be deployed, and management of the device is a serious challenge. So difficulty in large-scale deployment and maintenance, and blockchain can help to maintain all these security credentials, the firmware, the application, the device in a reliable and efficient manner. So blockchain can help, but how the blockchain is going to? You have to exploit the blockchain. Once you know the concept of the blockchain, then you can exploit how the blockchain can be used to provide this mechanism, to provide the device management. Then service management. The inefficient service, the IoT infrastructure has an inefficient service, indirect device usage, lack of flexibility in payment methods. So all problems are there. Then you can overcome through the blockchain. Blockchain enables a decentralized automatic service discovery. Look at service discovery. You need a service, then you have to query a service provider. And once you query a service provider, then you can get a response. After that, you can know that this particular service is available. So there is an indirect, or this is the inefficient way of querying the existing IoT infrastructure. So blockchain can help by means of decentralizing and automatic service discovery. This is allowing a reliable direct access to the IoT resources. The problem is this, that if you allowing a direct access to the IoT resources, then the security comes into the picture. I should have a position to directly access my IoT resources without compromising the security of my IoT system, and blockchain can provide that. Certain resources where security and efficiency can balance, then blockchain can support the micro-transaction for all the IoT devices. Let's look at security. What are the security challenges? Counterfeit problem. Counterfeit is a very serious problem, and it's every year the counterfeit problem is increasing. It's putting a unauthenticated device into the system, and there is no way to authenticate the device, whether it's a genuine or it's itself is not genuine. So counterfeit problem, lack of the communication security and data privacy. These are some security concerns, and a blockchain can provide a reliable prevalence tracking of the IoT device to solve the counterfeit problem. We look at the counterfeit problem and some techniques that exist. Proposed blockchain technique to solve the counterfeit problem. So you can also find out the new technique to come up with the counterfeit problem. Then refine the access management, data assurance, data privacy as introduced by the blockchain-based IoT. So what we discussed? We looked at the problems with the IoT infrastructure, and we looked at is there a way to solve this problem through a blockchain. So there is a way. It's not that all the solutions or all the problems can be solved by the blockchain. Some problems can be solved by the blockchain, some cannot be solved by the blockchain. Somewhere you can use the blockchain. In some of the scenarios, the blockchain is not advisable to use. So let's look at the blockchain part. So let's look at blockchain. So what's a blockchain? If you look at the concept, was first proposed in somewhere probably in 2010 by Satoshi. Why he proposed that there is a problem associated with the digital payment. The problem was with the double payment. The problem with the double payment, that means I had a coin, a digital coin or digital currency, and I pay one of the customer, or I purchase something, I pay you. Now the problem with this digital payment or the blockchain system is that once you pay it, the confirmation is not from immediately. If I had hard currency, I can give it to I can purchase anything to the hard currency. So something I am having, and the amount of money that I have is decreased by the amount of money that I purchase. It's straightforward. The problem with the blockchain or the digital payment system, that you pay something. right? But the confirm the transaction, it takes a potential amount of time. Now, during this period, the payment and the confirmation of the transaction, a user can make another payment using the same number of times. That's the problem. That was the problem, and Satoshi and they come up with a technique to overcome this double payment problem, double spending problem. So let's define what's the blockchain. Blockchain is many definitions, but all the definitions have the same meaning. A blockchain is a data structure which is a growing list of the data blocks. So basically, we can say in computer science terminology, it's basically linked list, and each node is a block in the list. And these data blocks are linked together such that all blocks cannot be removed. Look at once a block is entered into the chain, then you cannot alter the blocks and you cannot remove the blocks. You need a integrity of the data. So let's look at the second definition. So blockchain provides a distributed ledger, transparent distributed ledger. So it's a open distributed ledger that efficiently records the transaction between two persons in a verifiable and permanent. So it says transactions are recorded. So how the transactions are recorded? In a verifiable manner. That is, any transactions that made in a blockchain, it can be verified by anyone in the chain. So it's a verifiable. Recorded, it's a verifiable, and so there is a transparency. Once recorded, it's permanent. You cannot change. So once recorded, you cannot change it. So you cannot tamper the data. Each transaction is secured with digital signature that proves the authenticity. So we're looking at one point we say there's a problem with the transactions about the authenticity of the transactions. Now, when you have authenticity, either you can encrypt it or digitally sign, and we have a low cost low cost devices with low processing power, resource constrained devices. Then the digital signature encryption techniques is not feasible. So here, each transaction is secured with a digital signature that proves its authenticity. Each block contains a cryptographic hash of the previous block. So it's not only information about the current block, it has a pointer to the previous block. That is why there is called a link. So it's the previous block. There is a timestamp. Look at, in a blockchain, there is a problem. The problem with the data freshness. A sensor will generate a data. And how do you know when the data is generated? So this question comes with the data freshness. So there is a timestamp assigned with every block, and from this timestamp, you can know the freshness of the data, when the data was generated. And all transactions, so it contains block contains the transaction information, a pointer to the previous blocks, and there is timestamp with others to the every block. Let's look at the third definition of it. Blockchain is a blockchain technology is basically a software. So it says it's a software, but what this it does, basically it's a protocol for secure transfer of unique instances of value via the internet without running a third-party intermediary such as bank or the government. So let's look at the figure and the right-hand side of it, the last part of it. So you had a part of Bitcoin, and there is a infrastructure. The underlying infrastructure is the internet, and let's look at between these two. Bitcoin is a monetary transaction system, and underlying there is a blockchain that facilitate the transaction system. So these are the definitions of the blockchain, available definitions, and all of them almost say the same thing. So what technology is used? Let's understand what is the technology is used in blockchain. And a blockchain is not a one technology. It's a combination of multiple technologies. So blockchain is a combination of multiple technologies. It uses a cryptographic key. Uses a key pair, uses a private and public key. For sending data, the private key is used to sign it, and the user verify it using a public key. Look at it is a transparent key. The moment you say it is transparent, that means everybody can see it and verify it. Now, how the transactions are made in a blockchain? When somebody sends, he is going to put his signature. If uses his own private key, it's a digital signature scheme. Encryption scheme and digital signature scheme, the operator works in a different way. Encryption uses a public key of the recipient, and digital signature uses the private key of the sender. So here, every user or every entity in the chain has a PRO key, a public key. So whenever he sends, he puts his own signature. He put his signature, that means sign the data using his private key. Now, the moment he signs the data using the private key, now look at there is an intruder in between sitting in the middle. So what is the intruder? Unless he is a part of the system, then he cannot access it, because the public key is not be available to the intruder. Now, if the intruder gets the public key, probably he can manipulate. So sending the data private key is used, and verifying it the public key is used. So it uses a cryptographic key. Then the networking protocol is basically peer-to-peer protocol. That means you communicate along with your peers only. My peers are my neighboring nodes, so I communicate only with my peers. So whatever the information I had, I send to my peer, and my peer after verification he send it to the other his peers. And in this way, the data is proliferate in the entire network. So it's a peer-to-peer network, and a peer. So every peer is called a node in the network. And peer-to-peer network is a crucial part of secure blockchain processing. Look at any peer that receives, and he sends to his peer only after verification. If the verification fails, then it's going to drop. So it's secure. Then it's a uses a distributed ledger technology. So it's a blockchain. You can say it's a distributed, decentralized, transparent ledger technology. So it's a distributed ledger technology. What is a ledger? In the bank, people measure ledger, that every transaction is recorded. So here, every transaction, whatever transaction that you make, everything gets recorded, and that recorded in a block. So a ledger is a collection of shared, replicated, and synchronized data. So here, every data is shared. Now we looked at one problem with the IoT. The problem with the IoT was a privacy was an issue. So, moment you use a blockchain, then you need to have a mechanism to ensure the privacy. He said, it's shared. Whatever the data I had, I sent to my peers, and the peers will completely see whatever communications transaction I make. After that, we send it to the next peers. So the privacy is lost here. Now, moment you are using the blockchain and you say security, so you have to keep in mind that where is the privacy? Blockchain doesn't provide the privacy, so you have to find a mechanism to provide the privacy. We look at how the privacy is here. So every data is geographically spread over the various computing devices. So it's not if you have a data, then the data is completely broadcast. It's completely broadcast to the peers. So everyone has the same data, and everyone is actually seeing the same data. So you make any transaction. So if I make a payment for purchasing a cup of tea, then everyone in the network knows that I have actually purchased a cup of tea and how much amount of money I spent in purchasing a cup of tea. Everybody can see. So privacy is lost. But IoT needs the privacy. Now, when you are using a blockchain, then you have to keep in mind how the privacy is ensured using a blockchain technology. Any transaction approval and permission in blockchain is handled by the distributed network. Then it uses a mechanism, another technical question. Hashing is converting data in with variable length to a fixed length. Look at, we obtain data. All data is in a different format. Lengths are also different formats. Then uses a mechanism called hashing from variable data. So once you hash a data, then it generates a data of fixed value. So whether you use a hash of 256 or hash of 128. So it generates that number of bits. And it's a hashing is a one-way process. It acts as a verification of the transactions. This also ensures the integrity. Hashing also ensures also how the no transaction has been tampered with after it has been recorded in the blockchain. So these are the technologies that we use. That let's discuss. We talked about cryptographic hash. There is a immutable ledger. That means once written, you can undo it. So any transaction, if you paid the money and you thought that by mistake you have made it, you cannot undo it. It's simply not possible. Then it's a peer-to-peer network, and there is something to be done by mining. Mining is you had a blocks. Then who is going to create a block? You can look in a peer-to-peer network. No one is trusted ones. These all are untrusted nodes. You put a IoT device. You have a trusted IoT device is fine. If you do not trust the IoT devices, then there needs to be a mechanism for collecting the devices from mechanism for collecting the data from untrusted devices. In a blockchain, no nodes are trusted. They all are untrusted nodes. Then from these untrusted nodes, you collect the data and you bundle it into something called a block, put them into the block or the data that you pay transaction, put the transaction in a block, and there is someone called the miners. And the miners are actually responsible for forming the blocks and putting the blocks in the blockchain. So we'll discuss about how the mining is taking place. Then in the consensus. Now 10 people have there are 10 miners, let's say. So all 10 miners will generate a block. Then which block is going to be retained onto the blockchain? So there has to be some consensus mechanism among the untrusted. Look at the entire network is not trustworthy. Nodes are not trustworthy. They do not trust each other. But among them, with untrusted nodes, they come out with a consensus. Which particular block to create? So there is also consensus protocols. We look at these two, consensus and mining. So let's look at how the blockchain works. So once you know how the blockchain works, then you can apply the blockchain to any of these the security loopholes in the IoT infrastructure. A blockchain consists of three important concepts: one, blocks, nodes, and the miners. Every chain consists of multiple blocks. So it is a block, the chain. So there are multiple blocks in the chain. Then each block has three basic elements. One is a data in the block. So if transaction, so now we call the data in the block. Then there is something called a nonce. This is a 32-bit number. So we look at why the nonce is required. So a block is there. Block is nothing but the data. Data is nothing but all the transactions that we have made. Any transaction that we have made, that is put into we call it data. And there is a nonce. And this nonce is nothing but a random number. This is a random number, randomly generated number. A random generated when a block is created, which is then used, which is then generates a block made of hash. So basically, it's a random number, and this random number is used to generate an hash. We will discuss how this how this nonce is being used. Then there is a hash. So three terms. One is data. Data is nothing but all the transactions. Any transaction that you made, we call the data. There is a random number called the nonce, and there is a hash. Hash is hashing the entire block. You hash the entire block, then you generate a fixed length of the fixed length of bits, and that is your hash. So it's we use a SSA 256. So it generates a 256 bits number. And it starts with a large number of. So we'll look at how the hash is generated. Then the miners. So as I said, miners creates a new block on the chain through a process for the mining. So mining starts to be done by the miner. Once a block is mined and a miner becomes successful, then he can add the block into the chain. Then finally somebody is going to mine. Mining is a computational intensive. A lot of computation is to be done. When you do a lot of computation, you have to spend enough resources, enough computational power. When you have to spend enough computational power, you have to burn enough electricity. So when you burn enough electricity, you have to pay for it. Now, then why somebody should mine? So every miner gets a reward. So because they get a reward, so they mine. So let's look at a ecosystem. It's a Bitcoin ecosystem. Bitcoin itself is a blockchain. Ethereum is another blockchain. So it's a ecosystem. Let's look at this. So this is, if you look at inside the cloud, those are the nodes, and there are end users. Everyone can be end users. There are the service providers, Bitcoin service providers. Then there are the Bitcoin developers. And in this node, any node receives the transactions, verifies the transactions. After verifications, he sends it to the exchange. Let's look at it. This was about a payment in the Bitcoin. So there is a two-party, one is Alice and another Bob. And if you want to make a payment system, then the Alice will send the transaction to the nearest peers. So every user is connected to one of the nodes in the blockchain, the Bitcoin network. So we send it to the peers. What he does, he verifies the transaction. Now, how he verifies? This is a payment system. He verifies that the person who is making the transaction, he has enough money to make the transaction. Now, if he has enough money, then he verifies that this transaction is correct. Then after verification, he sends it to the peer. And finally, it goes down to the buffs, the peer. And once it goes to the buffs peer, then the transaction goes to the buff and close that the transaction is. Now, in between the transaction is gone. It looked at this pointer is not working. The transaction is moved from the live to the buff. Everybody has verified the transaction. Everybody has verified the transaction. The LIS is sent. It's not. It's A to B. The transaction from LIS to the buff. Every intermediate node has simply verified the transaction, forward the transaction. The transaction A is sending, the LIS is sending some money to the B. The LIS is sent. I have sent the money to the B. Bob has also received the transaction. Now the question is whether the transaction is committed or not. Either received. Bob has received the information that LIS has sent the money to me. Absolutely fine. Whether the money is actually recorded in the chain. Now, if the money is not recorded in the chain, then LIS can again spend the same. Then that's the double spending. So before this, there are miners. If you look at working on the side, there are miners. Then the miners actually take all the transactions. They form a block. Once they form a block, again they publish the block, and the block is again verified. Once it is verified, then it's added into the chain. And once it's added into the chain, then the transaction is complete. So Alliance has made a transaction to the Bob, and until the transaction is recorded in the chain, the transaction is not. So this is the issue here. The issue here, if you're using a blockchain, then in IoT, the IoT generates billions of data, huge volumes of data. So every data generated, you can think of as a transaction. The transactions is recorded, and until the transaction added in the chain, it's not complete. So how frequently the blocks is to be created, how frequently the transaction is to be committed. That's another serious. So let's look at how the blockchain is built. A blockchain is a chain of blocks. These blocks contains the transactions, and every transaction has a reference to the predecessor. So if you look at on the right hand side figure, these are the blocks, and every block has a reference to the previous block. And the reference comes through something called a hash. And each block has an implicit height that says how far it is from the first block, and the first block is called the genesis block, and the last block is the chain. So any block that is added at the end of the blockchain, this always called the chain diff, and the very first block in the blockchain is called the genesis block. And rest of the blocks structure depends on the genesis block. So each blocks also contain a block header to protect the integrity of the transaction and the blockchain. So look at the IoT system has the integrity problem, the data that you store. Now I can store, if I am going to store the data, put the data in a blockchain, then the entire integrity is maintained. Because He says the block header protects the integrity of the transaction. Every transaction that we made, every data that generated can be considered as the transactions, and once the transaction is headed, then the transaction cannot be changed. So integrity can be checked here. Each block contains one or more transaction in the block header, and the block header contains a. This is on the this looks at any of these is working. This is a block header. What does the block header contain? The block header contains the previous block header. It's a 2,202 times. We hash 2 times to generate a 250 bits of the previous header. And the combined S of the transaction in the block, the Merkle tree. Now, whatever the transactions you have generated, how do you ensure that the transaction is not going to change? Anybody can get into the network and you can change the transactions. If I am using it for IoT devices, then somebody can get into the network, somebody can change any of these transactions, then everything gets changes. Now here, it takes all the transactions. From these transactions, we generate one more hash, and we know that if any of the transactions we change, the hash immediately changes. So it creates a hash, and that hash is generated something in the Merkle tree. It also adds a timestamp. So timestamp which indicates the creation time of the creation time and a signature of the blocker. So everything is there. So generates a template block, a block without a signature. They collect the several transactions, put in the block, gets create a template, get whatever the transactions, put it in the block, generates a block header, creates the ID to the previous header. So you put a link to the previous block, so it generates the ID from the previous block using a double SHA-256. Pass through a SHA algorithm, 2 times it pass. It generates it 2 times it pass for a security purpose. No, nothing other than that. So it is SHA-256 or a double SHA-256. SHA-256 that you done once and generate a 256 bit. Double SHA says that pass through the SHA-256, you generate 256 bit. That 256 bit again pass through the SHA-256. That creates one more thing. That's called double SHA-256. And it creates a Merkle tree. Merkle tree is built using the transaction, the template block, and the time is set to the current time. The first time, look at, we are creating all the transactions, right? Somebody has to processing the transaction. Verifying, everyone is verifying the transactions, but somebody is processing the transaction. So when somebody is processing the transactions, then he say to process it, he has to ask for a certain fee, transaction fee. So in any block, you had a number of transactions that actually made, but there is one transaction, it's called the coin-based transaction. The coin-based transaction is not the transaction that is made. The coin-based transaction says how much fees that is going to charge for processing the transaction. So now let's look at signing the header. So let me. This is all the transactions. To sign the header using the private key. So you created the header. What does the header contain? Header contains the Merkle root, the Merkle tree. It contains a time. It contains another pointer to the previous block to which it is linked. So all these again signed to create one signature, and that signature is again the part of this part of the block. So if you look at on the right hand side figure, one is the pointer to the previous block. That's a double SH256. The middle one is a Merkle root. Is from the transaction which generates a Merkle root. That is basically nothing but a hash of all the transactions. And then the timestamp and signing which digitally signed, put a digital signature. Once the block is signed, it is available to all the verifiers. So you sign it, block is published. Now, once the block is published, the block is not going to edit to the chain. Other in the network has to accept that this is the acceptable block. Many may be doing the same thing. There may be many miners doing the same job. So this has to be accepted by most of the miners. If most of the miners accept this, then the block is added to the chip. Otherwise, the block is not added to the chip. So let's look at how this Merkle root is created, and this is where the integrity is maintained. Now let's look at this transaction. transactions, there are figures on the right hand side. All transactions are there. I had 4 transactions. There are 3 transactions. And there can be multiple transactions, but the first transaction is a coin-based transaction. We simply say that how much fees they are going to charge for putting the transaction. Look, you have made a transaction. There is many issues here also. You made a transaction. I am a minor, and I looked at your transactions, and you are paying me a less transaction fee. The processing charge is less, so I will discard it. Transaction. I will not put your transaction. In a scenario may happen that you made a transaction, none of the minor want to publish your transaction, put the transaction in the block. So there is another issue with the blockchain itself, and there are solutions to overcome this one. So we are not discussing on that part. So what I'm trying to explain here, that integrity can be checked. So you made any transaction, then finally you create a, on the top, you'll find a hash 256. 256 bits is generated from all this. There is a mechanism to do this. So all 256 is generated, and if any of the transaction is changed, then the 256 bits that is generated, that is going to change. 1 bit, the hash is designed so that if you change 1 bit, then hash of the chain, there will be a significant difference in the hash of the previous one and the chain. That's one of the properties of the hash algorithm. Hash functions. So this is what, let me skip this one. Then you generated a block, right? Whether the block to be added, unless there is a consensus among all the participating nodes, the block is not going to. So there has to be a consensus. There exists a consensus mechanism, and this consensus checks also adds the block, and it also checks the integrity. The consensus means agreement among the peers. So all the peers is to agree that some block is to be added. A block has to be added into the network. The consensus is the agreement among the full nodes about the next blocks to be added into the chain. Look at there can be 1,000 number of nodes. So all nodes are not minors. Everyone cannot be a minor. To become a minor, you must have a computational capability. You must have high computational capability. Then only you can become a minor. So one, it's a if a block is mined and it's published, then if it is agreed upon the most of the verifiers, most of the verifiers agree, yes, this is the block to be added. And this process ensures the integrity of the chain, and there are different consensus models. The proof of work, proof of authority, proof of stack. There is also called the Byzantine fault tolerant consensus. Now I'm not going into detail, but let's say what is the proof of work. The proof of work says, so we'll discuss on the proof of work. Proof of work says that you do some amount of, you compute something. Then if you are able to compute, then you win. If you are not able to compute, then you are not going to win. That way, here, if you want to add a block, you need to do a computation. That computation is it's a very enormous amount of computation has to be done. And if you are able to perform that computation at the earliest, then you win. So there is a Byzantine also there. And there are 3 types of the blockchain. It's a permission, it's the permissionless, and the private blockchain. In case permissionless, it's anyone can join and anyone can leave. You have the permission. That means you need not have to take a permission to join the network or leave the network. You can join and you can leave. Now, if you are using a permissionless blockchain for IoT system, then anybody can enter with the IoT system, anybody can leave from the IoT system. So you have to keep in mind that what type of blockchain you are using. And if you are using one type, then what mechanism is to be enforced for the access control. Then, in case of a permission, to join as well as to leave, you have to take a permission. And if it's a private, that means members the memberships are available to only few close groups. So let's look at this is of a Ethereum blockchain. Let's look at how a blockchain looks like. Now, if you look at from the left hand side, these are says the blocks. There is a block number. If you look at the miners, there are many miners. All miners may be mining, but the block mined by the all miners is not going to edit into the blockchain. Few of them, only one will be added into the blockchain, and it's a block number. This is a miner. If you look at the top one on the block, it says there are 142 transactions in the block, and the miner is determined, and it is taken 4 seconds to mine. But let's look at the block. The block that is added, it takes 51 seconds to add the block. So mining and adding the block just takes a amount. Now, if you look at on the transactions, every transaction is a transaction number, and every transaction is from the source. You make a transaction, you have to specify the source and to specify the destination. So there has to be address mechanism, source address and destination address. Now let's come back to the mining. How the mining is done. Now let's look at what does the a block contain. A block contains a data. A data but nothing but some transactions made. Then a block contains a hash to the previous block. So this is the hash of the previous block. Now here he says the hash begins with 4 zeros. These are all hexadecimal numbers. So first 16 bits are zeros. Now I will explain what is the first, why the first 16 bits are zero. Then it's a hash. Hash, you have to generate this hash. This hash is generated. Now if I compute, if I pass this one, the previous hash, the transaction through a hash function 256 bit hash, so I get a 256. Right? Now, if you look at my previous hash is 40, that means any hash that you generate must have at least 4 zero significant 16 bits. Significant bits should be 16 bits should be 0. So these are 4 zeros. First 16 bits should be 0. Now you pass through a hash function, you will get a 256 bits. But it does not ensure that the most significant 16 bits are 0. Now how to make the most significant 16 bits are 0? Now let's look at it. This data are fixed. Data are fixed. You have put some transaction, the transactions are fixed. You cannot change the transaction. Previous hash is fixed. You cannot change the previous hash. Whatever is the previous hash, that you, because that is the way you link to the chain. Those two data are fixed. Now, to generate, if I pass this one to any hash function, I will get a 256 bits. But what my requirement? My requirement is that most significant 16 bits should be 0. That is my requirement. So I need one more data, and that data is comes from something called a noise. So this comes noise. So you keep on changing the random number to generate a random number. So you keep generate a random number. Then with that random number, with the data previous is passed to hash function, you generate something. You will get definitely you get something. But my criteria says that the most significant 16 bits should be 0. That is what the problem of the proof of work. We are doing enough of computations where the computation says the most significant 16 bits should be 0. So there is a timestamp to get it. So let's go back. So let's come back to the blockchain and IoT application. Now, the blockchain it can be classified based on the consensus mechanism. We looked at the different consensus group of work, group of stack, Byzantine fault tolerant, all consensus mechanism. Either you can classify it on the basis of the consensus algorithm, or you can classify on the basis of the network access type. Network access type either it is permission or it can be permissionless. So this says that you can classify the blockchain, the proof of work, on the basis of the consensus algorithm, is a proof of work, proof of stake, Byzantine fault tolerant, or any other consensus algorithm. So every concept, look at the consensus algorithm itself is another resource issue in blockchain domain. How quickly you can generate a consensus among the users. Then it can be classified on the basis of the type of the access, whether it's the permission or it can be permissionless. And if you look at a multi-chain, multi-chain is the permission blockchain with proof of work consensus mechanism. And if you look at Bitcoin, Bitcoin is a permissionless the blockchain. It's a permission blockchain, and the consensus mechanism is a proof of work. Now, if you look at the outer one says the application where application of the blockchain. It can be applied to any domain. Now, if you look at the agriculture, In agriculture, you can apply the blockchain for the harvest prediction, or you can apply for farm monitoring. Then, if you look at the healthcare, it can use for drug management. So it can be used for a variety of applications. It all depends upon how you are going to use it. But I look at only one for IoT security. Blockchain is an ideal option to provide a decentralized experience. Look at traditionally blockchain has a centralized architecture, right? Traditionally blockchain is traditionally the IoT architecture is a centralized architecture, but blockchain can provide a decentralized security. The characteristics of high availability, tamper resistance, and transparency can fulfill the security requirement of the IoT infrastructure. See, it's all the blockchains. Anyone can access any information to the blockchain. Now, these blockchains, this also measures address the security concerns like the access control, data assurance, hardware counterfeit, and tampering, key management, and the trust. This is what we looked at. The problems associated with the building IoT infrastructure. Let's look at how each of this policy can be accessed, addressed by the blockchain. Access control. You can manage the access policy. Then you can preserve the privacy. If you look at the data assurance, we looked at the data integrity, data freshness, counterfeit. The counterfeit hardware through supply chain management. We can go for a device authentications, key management. Blockchain can provide for key freshness. Then you can have a transferable credential. Then the trust. Then you can have a trust computing base. Then you can go for registering for a cyber attack. Let's look at the password access control. How blockchain can be used as an access control. Now, you access the IoT infrastructure. The moment you access the IoT infrastructure, then you put a potential risk on the IoT infrastructure. Right? Thus, it's required how the device and data are being accessed directly determines the security of the system. Now, if you allow a user to directly access any of the IoT device, an intruder can also get into the system. Then there has to be a management control mechanism. Not everyone can get into the system. Some authenticated users can get into the system. Now, traditionally, the IoT infrastructure is a centralized infrastructure with a central access mechanism, and this central access mechanism has traditionally some weakness for it. The weakness of the centralized access control system is hard to achieve the security. End-to-end security is not possible. Then the centralized architecture is a single point of failure. If the central system fails, the availability fails, and all the security credentials also fails. User is not involved in the control of in a centralized architecture. Then every access is managed and controlled by a single entity, a central entity. So user is not involved in managing this. The central, if you are having a central service provider, then he can make some use of the data illegally. He can deny the use of some of the data. The central architecture are very expensive. It's expensive because it generates a huge volumes of data, and huge volume of data needs to be stored, and the security credential is to be already implemented. The central access system is not suited for IoT scenarios requiring device mobility and or the collaborative management. So if a device is mobile, so the central systems may fail to provide security to the system. Now let's look at what the blockchain can do. A blockchain-based access control has a better support for mobility, accessibility, scalability, and transparency. These are the features available in the blockchain that provides. Now, all the data inside the IoT network. Now let's look at how you are going to do this. You generate the IoT data, large volumes of data is generated. Then where do you record it? In a centralized traditional architecture, you put it in a central server. Now when you put it in a central server, single point of failure, your all your security credential, if the central server is compromised, the security credential also. Now, instead of putting in a central server, you record everything in a blockchain. Now, when you record in a blockchain, then anyone who is a part of the blockchain can access it. And you look at blockchain provides all this mechanism. So all data inside the IoT network can be recorded, verified, and managed by blockchain. Once you put it, then everything can be done by this blockchain. The privacy preserving for the IoT system. Now, you put the data. I said in one before that you put the data. You're using a blockchain, but you're using one information. That's the privacy clause. But everyone can see. There is a problem with this. So it's important to prevent the reading or leaking of others' data and configuring. Besides ensuring the availability and look at it ensures everything. Availability it ensures, accessibility it ensures, security it ensures. But whatever the problem with the privacy, privacy does not ensure. To ensure the privacy, another blockchain is performed. That's the interplanetary file system. IPS. This is designed to provide the privacy of the IoT. So privacy can also be preserved. Let's look at how it will do the data assurance. A blockchain is an appropriate technique to address the data provenance and the data integrity problem. Now, you put any data in the problem in the data in the blockchain. So any data in the blockchain, it cannot be tampered. So moment you tamper, we looked at the Merkle tree. The Merkle tree is immediately gets changed. Now, if the Merkle tree gets changed, then the entire header information gets changed. The hash information gets changed. So the entire tree becomes tree from where the node from where the data has been changed. This becomes invalid. So anyone in the chain can immediately detect that a tampering has been done. The hash function based chain system inherently address the data integrity. So this is basically you're generating hash. Then any change in the data, any tampering of the data is going to change the entire hash of the block. Then the timestamp, you're storing it and you're storing with the help of a timestamp. So timestamp is going to tell what is the freshness of the data, when that particular data is generated. The counterfeit is a very serious problem in the blockchain. And how do we manage it counterfeits? Now, this counterfeit device. So let's look at every user, or every manufacturer. They can register themselves into the blockchain, and any device that they generate, they will put it in the blockchain. So every device from the manufacturer is there in the blockchain. Now, when it's there in the blockchain, so any user or any customer can immediately get the information from the blockchain, whether this device is a genuine or it's a counterfeit. So all electronic parts, IoT device can be registered and managed and protected by the blockchain. So it creates everything you can create it. Once the device manufacturer, you put the device entire identity of the device in the blockchain. So once it's there in the blockchain, so anyone can look at the identity of the device. So no counterfeit device can get into the system. So what is you can have the origin of manufacture. Now the blockchain, if a device moves from the manufacturer to a retailer, the entire tracking information can be recorded in the blockchain. So from the customer point of view, he can track with the actual manufacturer of the device. So counterfeit can be tracked. So origin manufacturer, all the owners, the current owners, the previous owners. That means we're looking at the tracking of the entire, and all traces in the supply chain can be recorded in the blockchain. So any transaction from the source to the dealer, to the sub-dealer, to the customers, all transactions can be recorded, and anyone can verify the genuineness of any of the devices. Key management. The key used for any key that we use needs to be refreshed securely, adding to address the long-term security. So here you had a blockchain. Then you can divide the blockchain into different levels of the chain. The one chain can manage your key. You can identify a key along with the IDs of the device. A key and the ID. That combination is stored in a chain. When that combination is stored, then if you have a user who is accessible to the device, that means every user cannot access to the device. So any user who is accessible to the device, he can configure the device, he can change the key. So chain itself, remember the key, the identity of the entity who is going to use the key, the user who is going to use the device, and the user, if he has the permission in the blockchain, he can manipulate. So no third party can manipulate the keys in the chain. Then trust, and any adversary can easily disrupt the IoT system. He can install many number of devices. The trust of the system can be disrupted. So adversary can easily disrupt the trust in the IoT system by forging the identity or spoofing the identities. And blockchain is a suitable solution for trust management, and that we have seen the proof of work. What does the proof of work mechanism say? Proof of work mechanism says that to add a block into the chain, you have to do a certain amount of work, and that work is computational expense. And if somebody introduces once into the system, then we have to compute that amount of work, and that is a very massive amount of computation. It's not done by any ordinary user. You need to have a separate data, minus all values, separate data centers to compute all these parts, minus one. Now, so let's if you have a trust, then you can itself build a network. That means you had an IoT system where you can have a group of trusted people in the IoT system. Now, once you have a group of trusted people in the IoT system, you can make a group, and you can make members in the group, and you register the group into the blockchain. So once you register the group into the blockchain is the information of the group, the members of the group. Then in the blockchain, you can design a smart contract so that the member of the group can access the information in the chain, or the no members outside the group can get access into the blockchain. So there is a mechanism to provide it. Now let's look at what are the challenges. We look at there are solutions, but each blockchain is a solution for all problems in the IoT network. Blockchain is not a solution for all problems. Blockchain can supplement or sometimes can complement some of the problem, but it's not a solution for everything. So, if we have entities in the IoT network and all entities are trusted entities, if all entities are trusted, then blockchain may not be a solution. Or if the service is acceptable from a trusted central authority. That means look at it's a traditionally IoT architecture, it's a centralized architecture, and I am fine with the centralized architecture. I trust the centralized architecture, and I am fine with that. So need not have to go for a blockchain. If everything, the blockchain is basically for untrusted entities, not for the trusted entity. Then need for a data sharing. Now, if you do not want to share the data, if you have a private data. Look at the moment in a blockchain is a platform where everything can be shared. Now, if you say, I don't want to share my data, even the number of items is not to be shared, the hash of the data is not to be shared, then blockchain is not a suitable platform for you. But if you want, if you have data, and that need to share the data, and data need to share to a common platform, then blockchain is a suitable solution. Then it's not only sharing, there is a problem associated with the cost of the implementation. It generates, look at IoT generates the volumes of data. Then this data has to be stored somewhere. Now storing and processing. So it needs somewhere to be stored, data storage, and for data storage, the associated the corresponding cost. If you look at whether the storage, how to be the cost for storing a bit of information, that's also another issue. for storing, then the level of protection that we need, data protection. The another problem with the blockchain is with the throughput and the latency. Now, generates the volumes of data in the IoT, but this data if you are putting the data in the blockchain, there is a latency associated with every data generated into the put it into the chain, and the block generation and transactions processing speed of the blockchain increases the latency and impedes the throughput of the system that uses the blockchain. The currently you are using a Bitcoin blockchain. A Bitcoin blockchain takes around 10 minutes to generate a block, and to process one transaction it takes around 3 to 7 seconds. So within 10 minutes, volumes of data. What happens to the next volumes of data? You know. In every 10 minutes, one block is generated. When the volumes of data is generated, look at the rate at which the blocks need to be added. Now, if you are using Ethereum blocks, the Ethereum blocks takes around 17 seconds to add a block into the system. So it's all the rate at which the transaction need to be processed, the rate at which the transaction need to be processed, and the rate at which block need to be added into the chain. This also limits the acceptance, the adaptability of the blockchain. So it's not that blockchain can be applied everywhere. Blockchain is a solution, but if you look at whether your problem, the candidate solution is a blockchain or not. If it is a candidate solution, then you have to find out how the blockchain can be used. Find out a solution. So, if you have any question?
We reconstruct the data back again.
Where?
The data will process to the blockchain. Can
Right.
Again, the reconstruct.
Why you want to reconstruct? You know the data.
From one end, we are sending the data to the other end.
Right.
The other end, they are going to get the original data.
Yeah. Yes, everything is recorded in a chain. So any data you want, you can get it from the chain.
But you are adding some hashtag to the idea or
No, hashtag is only added at the header. Let me see.
the original data is not going to be.
No. Let's say I probably missed one point somewhere. So it's
It's for zeros in that data.
but let me, this is my transaction. If you look at TX my original transaction. Nothing is done in the original transaction. Now, if there is mechanism, suppose this transaction is visible to everyone. Everyone can see the transactions, right? Transparency, privacy is lost. So how do you achieve the privacy? So what I do, I encrypt all these transactions. Transaction encrypted, no one can see my transaction. Transaction is fine. Encrypted form is there, no one can see my transaction. Suppose the transaction is not. What we are going to generate? I am going to generate only the top 4 elements. In the block, the top one. One on the extreme left refers to the previous block. Next is the hash of the current block. Hash of the current block means the nonce data, and the data is the transaction and the previous hash all taken together. That generates. Then there is the time along with the timestamp and the final signature. So these transactions, lower part is nothing is done. Lower part is still there in the block. Lower part. What is that? The header part is you are creating. So if creating a block, you are adding a header of the block. So any transactions, if anyone changes any of the transactions, then header part is going to complete. Since the header part changes, then the entire block becomes simple. Starting from the block where the header is reached. So immediately anyone can know in the chain that something is wrong. That is why it provides the integrity of the system.
Sir, you told us many different and new things in blockchain. I have a few doubts. Like, sir, you told us about counterfeit hardware, and you also told us that discarded hardware became counterfeit sometimes.
Okay. Let's go back to the counterfeit. Counterfeit is a serious issue. There are techniques exist.
Sir, these counterfeits are sometimes the intense line.
Intense line.
And it also can be of, if some electronics hardware are discarded, then that is also creating counterfeit. So then, sir, how can we find it? How a person who is designing any circuit or something?
See, you design a sensor. Let's look at let's design some thermal sensor. Designing the thermal sensor is known to every manufacturer, right? Now, designing the sensor needs some components, and that component I can get it from some unused electronics component. You can use those components to build your sensor, and you are using those components, but those are not genuine ones. Those are already discarded, and using that. Somebody can launch because it has its own weakness in the hardware. Somebody can tamper that and get into the system, or the one who has itself built the counterfeit hardware instead of genuine one using the counterfeit hardware, they can themselves put a malware into it.
By generating.
Yes, to launch attack into the network. So this is very serious issue. So the blockchain says that every manufacturer you registered in the blockchain. So and whatever the device you produce, you generate one identity. Or you can one of the way you can generate the identity is the POP. Using the physically unclonable functions, generate a code. And that code you put it in the NAND. So anyone in the blockchain, so anyone can verify whether the product is genuine or not. So their mechanisms exist.
And you also told about peer-to-peer network,
Right.
and you also give an example of like if we are doing any transaction, first it will check that much of money is present
Right.
there or not, then it will go for the next stage.
Right.
Now, sir, my doubt is how it will create that block so that it will be uploaded. What this means, how the blocks are creating before uploading to the chain.
Okay. So what we said, you create one template, right? What does that block template says? Block template says there is a header. It's a data. There is a header of the hash of the previous block and a hash of the current block. Header is there. Header with some information. Hash of the previous, hash of the current. Then there is a timestamp and a digital signature. Then the template also says there is a data. Data is nothing but the transactions. Now this is available. Pointer is available. This lower part is known. All transactions are known, right? So a miner is mining the blocks. That means he is validating the transactions. So
Sir, who is the miner?
miner is one who is going to mine the blocks. And mining the block means taking the transactions, creating a block, and putting it in the chain.
You said that most of the energy is wasted in mining.
Mining. Mining is a computationally intensive one. Look at I said in one of the figure. If you look at the hash in the proof of work concept says that the most significant 16 bits of a hash to be shipped, right? So you give any data to a hash function, it will give a fixed amount of bits. This will move to a hash SHA 56, so it will give a 2. You write A, pass to SHA 256, it will generate 256. So what are the information available to me? The information available which are not going to change is the transactions are not going to change. Hash from the previous block is not going to change. Timestamp is not going to change. These are not going to change. Then I need a variable data. These are my fixed data. So I need a variable data. So where the variable data will come? The variable data will come only from a random number generator. Nonce is nothing but a random number. So you generate a random number and along with all the fixed data and a random number pass to the SHA 256. And look at what is there. Did you get the most significant 16 bits? No. Change the random number again. Change the nonce value. Pass through again. You check whether the most significant bits are 16. No. Again keep on. So it is computationally intensive. So everybody cannot become a miner. So it needs a lot of computation. It's not so it's not easy to generate a hash with you can generate a hash, but it's not easy to generate a hash where it specifies certain constraints. Verification becomes very easy. So once the hash is generated, then verifying is become very easy. The reverse process is
Assume like many miners are there, but any one will be
Right,
selected
right.
one. So that selected one will be which matching as
no. The miners, there are many miners, and they have to agree upon that which particular block to be added. There are many miners out there. So all of them mining, you are a miner, I am a miner, I have 5 transactions, you have 20 transactions, somebody has 3 transactions, somebody has 1 transaction. Everyone is mining. Everyone put into the mining block. But everybody wants a reward. Everybody wants a reward. Then among this, they have to reach a consensus among the consensus algorithm. There are different group of work in one consensus algorithm. Here group of work says anyone who has mined fast. It takes enormous computational time. Somebody has a massive has a data center with massive computational power. He can immediately generate a hash that satisfies the constraint. So he wins. So here also there is an issue. Somebody will take control over the blockchain. How he is going to control? He put massive amount of power, massive computational power. So any block he can generate a block very quickly. So he also comes. So there is another solution to this problem. Yes.
So while generating these random numbers, do we need to, from hardware aspects, do we need to take care of this linearity and non-linearity of the shift register? Does it has any effect in this?
Actually, I have absolutely no idea. It's simply a random. How you generate a random number is
Yeah, because from hardware aspects we take care of that.
yeah. CB says it's a random number, but how the random number is generated it all depends on how you generate.
Then here also it is previous has and has. So this is the third block. For the fourth block, this has will be the previous has.
This the hash is pointer doesn't work here. So whatever the hash you generate, look at block 3, a nonce is done, you put a nonce, then the transaction data and the previous hash, all take along with the timestamp. The timestamp is the timestamp, the time at which the block is created. That is the timestamp. And there is a mechanism to put the timestamp also.
What will be the previous has for the next block?
Which one? For the hash that you generate. The hash that you generate here.
You have to make this first 4 digits 0.
Right.
We
The
intentionally.
first 4 digits, so you have to generate a hash such that the first 4 hexadecimal digits is 0 or first that is 0. That will become the hash of the previous set of the block.
Then that will be like.
They look at the blocks are linked to this hash only. Cryptography hash.
In this coin to coin transaction also the each coin is having different hash.
Each coin. Let's go back. No. Let's look at here. Each coin is having the hash is there. Same. This is my block. If you look at in one place, this block is created. That is Rick. That is Rick to Mike. Rick to Elias. Another block is William to Lisa, and another is Lisa to Bob. So this block again the same information. The operation principle is remain the same.
For generating a private key and public key, how we can use a random number?
You are not generating private key and public key is a random number. The public key generation has to be done in a different manner. And those public key in blockchain are generated. The private key is a public key and a private key. There is a mechanism to generate the key. Not from random number. It's not from a random. There is a completely different mechanism to generate this key, especially in the blockchain.
Random number used only.
Random number is only for this computing the hash. No else.
Participant, I am just asking if they Hello, who is online? Pratik and Dr. Joshi, do you have any question? Because we are towards the end of this session. To minimize. We are towards the end of this session. I thank Professor Ashok Kumar Guru sir. He has given his valuable time for us. I know sir from 97 actually. He is also my teacher. Because when I used to do diploma in India, one state government college, I used to teach us one to have sir has taken on basic global programs I made. So I saw him basic teaching research in this local area. At the same time, we also count sir one of the good teacher in this department, apart from other few teachers are there. So we are also trying to do certain work in FPG implementation of blockchain for electronic health record from 1 year, and last year we did SHA 512 implementation through Verilog. And this year we are trying to learn and do something on this now random generation, which will be FPGA based, Verilog based. So that's why I have a particular interest in this topic. So thank you, sir, for your kindness to give us time so that our participants are mostly will be share our discourse. Actually, in hardware security, no doubt we are securing hardware through certain mechanism, but at the same time, when it is cloud and it is open to network, so we need blockchain methodology and similar methodology like cryptography and all. So we have done 2 courses on software security by Professor Anirban Sekupta and Professor Upi Chatterjee from Kanpur in hardware security. So this is part of another course by Dhruv sir. So we thank him for his presence here, and thank you sir for coming. Thank you. So again,